Question 11. Which statement is correct for the distribution curve of molecular energies in the gas, sometimes called the Maxwell-Boltzmann distribution curve? The curve is symmetrical about the maximum. So I've got a curve here. Is it symmetrical? It's symmetrical. No, it seems to tail off over onto the right-hand side. It could even come further across this way if it wanted to. So it's not symmetrical. You couldn't put a mirror image down the middle. There are always some molecules with zero energy. No, it goes through 0, 0. So all of the curves go through 0, 0. So there are no molecules with zero energy. You'd have to get down to a temperature which is not feasible, called absolute zero, to stop particles from moving and give them zero energy, and that's not possible. So B is your answer, but let me just explain C and D. The position of the maximum of the curve is not dependent upon the temperature. It is, because as you increase the temperature, it shifts towards the right hand side. The peak level comes down because the area underneath the curve, which it represents the total number of particles in the gas, stays the same as long as it's a sealed vessel. But so the blue one is cold, then the green one is medium temperature, and then the red one is a hot one. Don't quite like that drawing. I took it from the internet. Really what should happen is on the right hand side, they should never go back to zero. There's always some particles on the right hand side of the curve that have a high energy, but it's not a bad representation in terms of the lower temperature, the peak shifting to the left hand side, going further to the left, and at the higher temperature going to the right hand side, and becoming a higher peak on a colder temperature, because, as I say, the area underneath the curve is staying the same. So the position of the maximum is not dependent on the temperature. Yes, it is. The maximum peak shifts to the right hand side as you increase the temperature, or shifts to the left hand side as you lower the temperature. The mean energy of the molecules is greater than the most probable energy of the molecules. So the most probable energy of the molecules, if you draw a line down from the peak where it hits the x-axis, the energy here, that's the most probable energy, where most of the particles seem to be. They have that energy, but the mean energy is the blue line, and that hits it at a slightly higher energy value is the mean, or the average, which is slightly to the right. So the mean energy of the molecules is greater than the most probable energy of the molecules. D is right as well. So the one that's incorrect is answer B, because there are no particles with no energy. So B is wrong. When 1 mole of ammonia is heated to a given temperature, 50% of it dissociates and the following equilibrium is established. What is the total amount of moles of gas in the equilibrium mixture? So 1 mole of ammonia makes half a mole of N2 and 3/2, which is 1.5 H2. So if 1 mole of ammonia reacts, it makes half a mole of nitrogen and 1.5 moles of hydrogen. But it actually says only 50% of it dissociates. So 50%, only half of a mole of ammonia is dissociating. So 1 mole of ammonia makes 0.5 moles of N2 and 1.5 moles of H2. If half a mole of ammonia reacts, it makes half that amount. Half of 0.5 is 0.25. Half of 1.5 is 0.75. So you might be tempted to say, okay, well, that's how much is made. 0.25 and 0.75 is 1 mole of gas that's made. And you might be tempted to choose 1 mole of gas. Luckily, it's not on the list. So you realise you've done something wrong, and at that point you realise that if 50% of this ammonia is dissociated, then half a mole, half of it's remaining, so 0.5 moles of ammonia are actually still in the mixture. They've never reacted at all, so you've got to add 0.5 on 1.5. The answer is A. Which compound is not an isomer of the following compound? So on each corner of this molecule is a carbon with hydrogen. So we've got C, 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 C. I've got 4 C's in there, and every carbon, because it's got single bonds, it's got 2 hydrogens. Every carbon needs 4 bonds, so it's got 1, 2, it must have 2 hydrogens. So I've got CH2, a CH2, a CH2, and a CH2 at each of those corners, and an oxygen. So my molecular formula is C4H8O. So I'm basically choosing which one doesn't add up to C4H8O, and my answer is D, which is C4H6O if I count up the number of carbons, hydrogens and oxygens. The answer is